In Module 3, Lesson 3, we're going to practice writing products as sums and sums as products. So our opening exercise, we're asked to solve this problem using a tape diagram. The sum of money was shared between George and Brian in a ratio of 3 to 4. If the sum of the money was $56, how much did George get? So in order to use a tape diagram, we're going to have to make a tape for George and a tape for Brian. So we have George and Brian, and I made George's smaller because it says the ratio is 3 to 4. So now we're going to divide these pieces into pieces, these tapes into pieces. George has 3 pieces. I know that because ratios are in a particular order, the same order that you are naming the people or the items. So George is related to 3 and Brian is related to 4. So I'll make Brian's tape into 4 pieces. The next piece of information they gave us is that the sum of money was $56. So this sum of money, which was shared between George and Brian, is a total of $56. And I would represent that with a brace and the $56 amount. But what we're really looking to do right now is to write an equation from the tape diagram. A tape diagram is good because it shows you equal pieces. So there are 3 plus 4 equal pieces, 7 equal pieces. And we want to know how much each piece is. So 7 times some number, n, equals 56. And then we can easily solve that by dividing 56 by 7. And we know then that 7, or the n, equals 8. So each piece is 8. But that's not how much George got. George got 8 times 3. So the answer to our question, George got 8 times 3, $24. So we have to make sure after we set up and solve our equation that we actually solve the problem that they asked as well, which is not always just the answer to the equation. In example 1, we're going to take the tape diagram concept and we're going to expand it so that we can use it for a lot of different things. So in the first step, they want us to represent 3 plus 2 using squares for units. And we can see that I started with 3 squares and added 2 more squares, and we know that 3 plus 2 then equals 5. Taking that same concept, we're going to now represent x plus 2 using the same size square for a unit as above. So in this case then, x is some amount, and then 2 more. So we notice in the x portion, we don't have that divided because we don't really know how much that is. But we do know that the 2 are going to be added to whatever that number is. Next, we're going to draw a rectangular array for 3 times the quantity 3 plus 2. So what we're really going to do is take this set of 5 and we're going to make 3 rows of it. So we can see that each row has 3 plus 2, just like we did up on the top, and there are 3 rows of them. Finally, we're going to draw an array for 3 times x plus 2. So we'll take this diagram and we'll make 3 rows of it. And our final representation, we have 3 rows of x, we don't know what goes in x, plus 2. Please notice when we do that, we would have 3 times x and 3 times 2, which is 6. So this is also representing the distributive property. 3 times x, which is 3x, and 3 times 2, which is 6. The distributive property, when it's written in its formula, is A times the quantity B plus C, and that would be then A times B plus A times C. So using that property, we're going to solve the next problem. If I have an array that is 16 plus 5, and there are 11 units, it's 11 units deep, then to find out this space, I would multiply 11 times 16. Which is 176. And 11 times 5, which is 55. Now we could draw lines and divide these rectangles into all that many squares, but it is definitely more efficient to multiply the numbers. Example 3, find an equivalent expression by modeling with a rectangular array and applying the distributive property for 8x plus 3, or 5 times 8x plus 3. To make our tape diagram less complicated, I just drew a rectangle, a little fatter so it represents something a little bigger, and I labeled the 5, that's how many rows we would have, and the 8x piece and the 3 piece. Now, using the distributive property, all we'll need to do is multiply 5 times 8x and 5 times 3. So 5 times 8x is 40x, and 5 times 3 is 15. And then we will rewrite this expression, 40x plus 15, and that's our equivalent expression. In exercise 2, we're asked to draw a model for each expression and apply the distributive property to expand it. Then we'll substitute the numerical values to demonstrate that they are equivalent. So we're going to start off with an array. So my array I showed as 2 deep, and the larger portion we're calling x, and this small portion is 1. So this is 2 times x plus 1. Now if we distribute, this would be 2 times x, which is 2x, and then the smaller piece was 2 times 1, which is 2. Let's rewrite that expression, 2x plus 2. And then we were asked to make x equals 5 to demonstrate equivalency. In other words, we're going to substitute 5 for x to show that it is true. So if x is 5, that would be 2 times 5 plus 2. 2 times 5 is 10, plus 2 more is 12. So here's our equation, or the solution to our expression. And then if we were to substitute 5 for x in our tape diagram, 2 times 5 is 10, and 10 plus 2 is 12. That's how we demonstrate equivalency. The second expression was 10 times 2c plus 5. So again, we'll draw the tape diagram. And our tape diagram is 10 deep and 2c plus 5 long. So now we will write we'll use the distributive property to multiply the two terms, 10 times 2c, which is 20c, and 10 times 5, which is 50. Then we'll rewrite that expression. 20c plus 50 is our expression. And then we'll substitute if c is equal to 1. (20 times 1 plus 50 equals 70. And then we'll substitute over in our tape diagram. And if c is 1, 20 times 1 equals 20 plus 50 is 70. So they are equivalent. Next, now that we have proven with tape diagrams, we're going to apply the distributive property and just do the math, and then we'll substitute to show equivalency. So 3 times 4f minus 1 would be 3 times 4f, which is 12f. 3 times 1 is 3, and we have a subtraction sign there, so it's going to be 12f minus 3. Then we'll substitute if f is equal to 2. 12 times 2 minus 3 would be 24 minus 3, which is 21. And our next problem, 9 times negative 3r minus 11. So 9 times negative 3r is negative 27r. Then we're multiplying 9 times 11, and then we have a subtraction symbol there. So 9 times 11 is 99. So this will be negative 27r minus 99. If the signs confuse you, you can always rewrite this as addition, and then you'll be able to multiply the two numbers and it will make more sense to you. Let me show you an example. So I would first rewrite the expression negative 3r plus negative 11. And then I would distribute, and I would have 9 times negative 3r, which is negative 27r, plus 9 times negative 11, which is negative 99. So in this case, it would look slightly different, but it would still be equivalent to negative 27 minus 99. Either way, you are looking at the same expression. Then we'll substitute if r is equal to 10, negative 27 times 10 minus 99. And negative 27 times 10 is negative 270. And we're subtracting 99. Now this might be a place where you get confused by it as well. And again, you can rewrite this as addition. Negative 270 plus the opposite of 99, which is negative 99. And then it will be easier to see that you are adding these two numbers together because they have the same sign. So when you add them together, you'll keep the sign, and you will get negative 369. Example 4, we're going to rewrite the expression 6x plus 15 divided by 3 as a sum using the distributive property. So step 1 was to rewrite the divided by 3 as times 1/3. So now we have 6x plus 15 times 1/3. To use the distributive property, what we're going to do is multiply 1/3 times each of the terms in the parentheses. You may be thrown off by the fact that this multiplication is written after the parentheses, but multiplication can be done either way. It is commutative. So we can take, this is a quantity here in parentheses, so we're not dealing with that plus sign yet. But we can take this 1/3 and put it in front of the parentheses, and it is the same either way. And that is exactly what we've done in the next step. We've distributed 6x times 1/3 plus 15 times 1/3. And then, solving those, 6x times 1/3 is 2x, plus 15 times 1/3, which is 5. And there it is, a sum, using the distributive property. Now let's do the same thing in exercise 3. First thing we'll do, 2b plus 12 divided by 2, is we will rewrite the division as multiplication of the reciprocal. So we'll have 2b plus 12 times 1/2. Then we'll distribute 2b times 1/2 plus 12 times 1/2. I'll put those in parentheses so that we can see them better and we can work with them better. Then we solve 2b times 1/2 is 1b, or b, plus 12 times 1/2, which is 6. Next one, 20r minus 8 divided by 4. So we're going to rewrite the division as multiplication of the reciprocal. Then we'll distribute the 1/4. 20r times 1/4. Oh, this is subtraction, minus 8 times 1/4. Solve those parentheses first. 20r times 1/4 is 5r. Minus, don't lose track of your sign, 8 times 1/4, which is 2. And finally, 49g minus 7 divided by 7. So let's rewrite it first. 49g minus 7 times 1/7, the reciprocal. Then we'll distribute 49g times 1/7. And we have a subtraction sign there, minus 7 times 1/7. And 49g times 1/7 is 7g. And 7 times 1/7 is 1. So 7g minus 1. In example 5, we're going to expand the expression. In other words, we're going to distribute. And you'll notice in this problem that there are 3 terms inside the parentheses. It really doesn't matter how many terms are inside the parentheses. You still distribute to each term inside the parentheses. So we're going to be doing 4 times x, 4 times y, and 4 times z. And it's expanded. In exercise 4, we're asked to expand the expression from a product to a sum. so as to remove grouping symbols. Grouping symbols are the parentheses. And they asked us to do that using an area model and the repeated use of the distributive property. So we're going to draw the area model, the array, in the same way that we did before, but now our array is going to have 3 terms in each row, the x, the 2y, and the 5z, and it'll be 3 deep. So there's our array, 3 deep, and it's x plus 2y plus 5z. Now we'll expand using the distributive property. 3 times x is 3x. 3 times 2y is 6y. And 3 times 5z is 15z. And then we'll rewrite our expression now. 3x plus 6y plus 15z. Our final example is a real-world problem where we're talking about a square fountain area with a side length, which is s, this is an s, which is bordered by a single row of square tiles that we can see in blue. We need to express the total number of tiles needed in terms of s 3 different ways. Now the first thing I want us to notice is that this s feet, this square area, is the interior of the tiled space. So if we simply take 4 times s, that is only going to account, and let's draw some lines to show that. That's only going to account for this space. Okay, so we look at that. This is s feet long, this is s feet long, this is s feet long, and this is s feet long. But we have one little square, and this little diagram tells us that. We have this little square area, which is 1. The side length of this square is 1. So there are a variety of different ways we can write this, and that's exactly what they want us to do. First of all, we could write 4 times s, right? 1, 2, 3, 4, plus 4 because we have these 4 pieces. We could also write it as 4 times s plus 1 because we have this space, right? S plus 1 to here, and then this one s plus 1 to here, this one s plus 1, and this one s plus 1. So 4 times s plus 1. Or we could really expand it and do s plus s plus s plus s plus 1 plus 1 plus 1 plus 1. And that accounts for all of that space. When you do these problems, until you are very strong in your understanding of the distributive property, drawing the array, drawing the picture, can be very helpful in your understanding how it works and why it works. And ultimately, that's your goal. You want to make sure that you can do this mathematically because you understand it in terms of what's actually happening.